give you the parametric equations, the work should be strictly following the formula. So if I have RT is given by sine t, cosine t, and t, where t goes from 0 to 2 pi, where my function f, the vector field is given by 6z, 6x, and 6y. Again, I want to compute the line integral of this function. Okay? Because overall, you have to use this parametric equation 2 times. It is best to separate these 2 steps. So this is what we did here. Okay? In one step, I'm simply taking the derivative. On the following step, I'm plugging in. Okay? So you can do this combining these 2 into one step, but sometimes you get confused. So simply do this separately. Because I have to use that twice. So one, I'm just taking the derivative. The other one, I'm going to plug in whatever is for x, y, and z. So still, I want to ask you a sort of irrelevant question. What does this curve define? Circle. If you're only looking at x, y, it is going to be a circle, which means if you press everything back into xy plane, you're getting a circle. But you also have a t variable in z. We actually talked about this before. Cylinder is a surface. It's not strictly speaking of a curve, right? This one will lie on a cylinder, I agree with you. So we actually studied this before. This is a spring looking like a curve, right? So a helix. This is a helix. So if you want to have a not perfect picture here, so this is going to be what it looks like. When t is equal to 0, x is equal to 0, so I have to begin with y. Okay, so this will be what it looks like. This is because I only have t between 0 and 2 pi. So if you don't have any restriction on t, you're getting an infinite spring looking like a shape. Okay, again, your calculus skill is independent of your drawing skills. You don't have to worry about what the picture looks like. You can still do the required computation here. Okay? So first, I simply go from 0 to 2 pi. Okay? And then I'm going to go 6z, 6x, and 6y as my vector field. Okay? So you have to use it 2 times. So first time I'm taking the derivative. The derivative of this vector field is given by, derivative of this
cosine t
is cosine t minus sine t and 1. And second, I have to use it second time. I have to replace x, y, z by whatever is needed here. So this step, you have to be super careful here. This is x, this is y, and this is z. Okay? So the first component, the x component is actually defined by 6t, z, so which I have to plug in t right here. So it's going to be 6t. Second component, the y component, is defined by 6y, so I have to take 6 times sine t. Am I right? Because x is defined by sine t, so it's going to be 6 sine t. And the z component of the vector field is defined by 6 times y, which I have to use cosine t here. Times cosine t minus sine t and 1. You see, the computation is pretty straightforward, but you gotta have to be cautious throughout this vector calculus. Okay, throughout this vector calculus, as long as you're careful enough, it should be pretty good. Then I combine everything here, so it's going to be from 0 to 2 pi. I have a 6t cosine t minus 6 sine squared t and plus 6 cosine t, 3t. Okay? And these ones are all linearly combined together, so I can break them down. So this is going to be 6 from 0 to 2 pi t cosine t, 3t, minus 6 from 0 to 2 pi sine squared t, plus 6 from 0 to 2 pi cosine t, 3t. So this is our practice of trigonometry integrals. I immediately know this guy equal to 0. This guy is definitely equal to 0. One thing you can compute is the antiderivative sine t. Evaluated at 0, which is 0, evaluated at 2 pi is still 0. So this guy disappears. The other way you can understand this is cosine and sine, they have a period of 2 pi. The integral of cosine or sine with respect to any multiple of periods is always going to be 0. So this guy is actually 0. But I have to do a little work for the first one. T cosine t, I have to do a change a variable or different parts. We haven't been practicing that too much. So this is what I prefer. So I will simply write down cosine t into d sine t. Is this how you learn about the integration by parts before?
No.
UV,
You have UV
UV minus integration
UV minus integral of dv.
Uh-huh. So you're using u dv plus v du is equal to uv. Am I right?
No.
That's what you have. That's the same thing, but you can move terms around.
Minus dv.
Well, you can move terms around to get the minus sign right here. But this is basically the formula you're using. Or if you want to have this guy, so this is u dv is going to be equal to uv minus v du. Is this what you learned before? Oh, sorry. There's no integration here. Yeah. They really should be whatever. Yeah, I'm sorry. Yeah, this is what you learned before, right?
Mm-hmm.
Okay, then I'm using the same formula here. I simply rewrite this guy as d sine t. So this is my v, this is my u. Right? So this is u dv. Then I can simply write it as whatever is needed here. Second thing, I have to deal with sine squared t. Sine squared t is pretty hard to find the antiderivative. However, I can still find its antiderivative if I have a double angle formula. All right, sine squared is equal to half of 1 minus cosine 2t. I'm using cosine 2t is equal to 1 minus 2 sine squared t. This is the formula I'm using. So sine squared t is going to be half of 1 minus cosine 2t here. Okay? So this one I already taken care of. Okay? So this is where I use a double angle formula. This is where I use integration by parts. Okay? You should know both of that before, but I want to recall what we have here. So here I have u is equal to t, v is equal to sine t, so I need to have t sine t evaluated from 0 to 2 pi minus from 0 to 2 pi sine t dt. Okay? Am I right? So this is uv evaluated between 0 and 2 pi, then taking the integral of v du. Right? V du. And then minus 6 from 0 to 2 pi, 1/2. Then minus from 0 to 2 pi, half of cosine 2t dt. Okay? I'm simply breaking down this into 1/2 minus half of cosine 2t. This guy is equal to 0. This is also equal to 0. This is also equal to 0. Cosine 2t has period pi. Essentially, you're taking this integral in 2 periods. So this is still equal to 0. So the only non-zero part is this one. Integrating from 0 to 2 pi of 1/2, you're getting a pi multiplied by 6. So in the end, it's just a minus 6 pi. Okay? Minus 6 pi. Okay, if you are not completely remembering every integration skills here or technicals here, you can review afterwards. I use basically 3 things. First, I claim the integration of sine or cosine within 1 period is equal to 0. This can be easily said by doing the actual integration. The other thing I'm using is a double angle function for trigonometry. And one more thing I used here is the integration of the parts. Okay? Okay, so again, if you're wondering what the heck is this minus 6 pi telling me, okay? If you want to translate this into a working force analogy, if you have this curve in a space and there's some moving object restricted on this curve, and you're pulling this object according to this vector field, then in the end, not only you don't do any positive work, you're actually dragging it backwards. That's basically what it says. Okay, the work you have done is minus 6 pi. So for instance, if you take in any fundamental physics, you can compute the kinetic energy, right? If you have a kinetic energy at a beginning point, if you use this force to drag it down, after t from 0 to 2 pi, the kinetic energy will be deduced by 6 pi, okay? Because this is the work you done to make the kinetic energy, or to make the moving object moving more slowly. Okay, that's basically what it is. Any other questions? So this is a very nice example we can practice. Not only we see all the fundamental theories, but also we see some integration skills practiced here. So next, I want to return back. I missed several steps here. If strictly speaking, you should evaluate what this is, and then you should see what this guy is. You should evaluate what this is. But what I'm saying here is, after you do some actual work, all these three components are all 0. Okay, that's why in the end I'm getting a minus 6 pi. But if you're not fully convinced, and I highly suggest you do the actual work in test and final, it's simply just evaluate what they are. Okay, it's not going to take you a whole lot of time. So next, I want to return back to our major topic today, which is conservative vector fields. Okay, conservative vector fields is really a very amazing topic. Okay? Conservative vector fields, as I said in the very beginning, only constitute a small proportion of all the vector fields. Okay? So among all the vector fields, only a very small subset of them is actually conservative. So first, I want to define what a conservative is. And we actually already saw that a vector field F, let's say I have a component F, E, H, is said to be conservative. If F is equal to a gradient of phi, okay, where phi is a scalar function, where you're going to see clearly what it is. So phi x, y, z is a scalar function. In other words, I can rewrite this vector field to be F, E, H, and it is equal to phi x, phi y, and phi z. Okay? In other words, this is equivalent of saying F is equal to phi x, G is equal to phi y, and H is equal to phi z. All right? That's one. So in R3, if I say a vector field is conservative, essentially I give you 3 conditions. Essentially, I'm saying the x component is the x derivative of some function. Y component of this vector field is the y derivative of some function, and H, the z component, is the z component, is the z derivative of the function. Now with me? So essentially, if I say a vector field is conservative, I'm essentially saying the 3 components are the partial derivatives of a function, respectively. Okay? So in R2, it might be easier. So I want to talk about R2 a little bit, so we can have a rough idea of how do we see if a vector field can be written down. If I have a vector field in R2, and it can be written as phi x and phi y. Let's say if a vector field can be written as these two components. X component is phi x, y component is phi y. We are using these notations to denote the partial derivatives. Everything? So we have discussed it at the front. And this is a pretty energy saving one. So if I have this representation, we have the property that if I take the second order derivative and I interchange the order, I'm supposed to end up with the same function. All right? The second order derivative, you can interchange the order. If this is true, then according to this formula, f is equal to phi x. So phi xy is to take the partial derivative with respect to y to f. Can you see that? So phi xy is equal to partial y to phi x. All right? This one is taking the derivative of x first and then taking the derivative with respect to y. Essentially, I'm taking partial y hating on phi x. Phi x, because this is a conservative vector field, it is equal to the x component, which is a small f. That's why it is essentially equal to f x. I'm sorry, fy. Yes? Similarly, this guy is equal to partial x hating on phi y, so this is equal to g of x. So if a vector field is conservative, according to this law, I have to make sure these two are equal. I have to make sure this is equal. So this is a necessary condition for a vector field to be conservative. In other words, if a vector field is conservative, then I take the symmetric derivatives. These two derivatives should be equal. I take the y derivative to x component should be equal to the y derivative of, the x derivative of the y component. Everything? So if a vector field is conservative, then the x derivative of the y derivative of x component equals the x derivative of a y component. All right? So I want to go back to the very first example we had, the radial vector field. This is the x component. This is the y component. This taking the derivative with respect to y is equal to 0. This derivative taken with respect to x is also 0. This is f, this is t. So f sub y is equal to 0.